All right, today we are diving into one of the most bizarre, most mind-bending results in all of mathematics. It's called the Banach-Tarski Paradox, and honestly, it's a concept that seems to just completely fly in the face of reality as we know it.
And I'm not exaggerating. As you can see from this quote, the theorem feels less like something from a math textbook and more like something out of a fantasy novel. It is a mathematical truth that just sounds completely and utterly impossible.
So let's get right to the heart of it. Here's the core claim. Imagine you have a solid gold ball. The theorem says you can cut it into a few pieces, move those pieces around, and put them back together to create two brand new, identical gold balls. No tricks, no extra gold. I mean, how on earth is that possible? Well, this mathematical bombshell was dropped back in 1924 by two Polish mathematicians, Stefan Banach and Alfred Tarski. And when they published it, it didn't just raise eyebrows. It pretty much ignited what you could call a scandal in the world of mathematics. The statement itself is shockingly simple. No fine print, no asterisks. You take a solid ball, break it into a finite number of parts, and then reassemble them just by rotating and moving them into two perfect copies. Now, our intuition screams that this is wrong, right? If you cut up an orange, the pieces add up to one orange, not two. So what is going on here?
The secret weapon, the key that unlocks this piece of mathematical magic, is a single, seemingly innocent rule that actually supports a ton of modern math. It's called the Axiom of Choice.
On the surface, this sounds totally obvious, right? If you have a bunch of baskets and each one has at least one apple in it, of course you can take one apple from each basket. But the Axiom of Choice goes way further. It says you can do this even if you have an infinite number of baskets and even if you have no describable rule for which apple to pick. It's a subtle idea, but it's incredibly powerful.
This comparison just nails the difference. Choosing a left shoe from every pair in a store? Easy. You have a clear rule. Pick the left one. But the Axiom of Choice lets you make infinite choices all at once, without any rule at all. It's like reaching into an infinite, chaotic jumble of things and just declaring, yep, I've got one from each pile, without being able to explain how you picked them.
And it's this power, this ability to choose without a rule that allows for the creation of things that just couldn't exist otherwise. These are called non-measurable sets. They aren't solid chunks. They're more like these unimaginable, scattered clouds of individual points. They are so porous, so strangely distributed, that the very concept of volume just doesn't apply to them. They have no volume to begin with.
Okay, so we have these bizarre, volumeless pieces. How in the world do they double a sphere? Well, the mechanism comes from some pretty high-level abstract algebra, but we can get the basic idea with a simple analogy I like to call the infinite dictionary trick.
So imagine a dictionary that contains every word you could possibly make with the letters of the alphabet. It's infinitely long. Now, what if you take out all the words that start with A? You're still left with an infinite dictionary, right? Well, here's the trick. You can take that A-list dictionary, do a simple little shift, and magically regenerate the entire original set of words plus some extra. You're basically using the weirdness of infinity to create something out of what seems like nothing. And this is exactly what's happening with the sphere. Mathematicians use this same algebraic trick, but not with words. They apply it to the infinite set of all the possible ways you can rotate a sphere. By splitting those rotations into different groups and shifting one group around, they can perfectly fill in all the gaps to create two complete sets of rotations from the first one. And those sets of rotations are what define our bizarre point cloud pieces.
So we've got our key ingredients. We have the Axiom of Choice. We have these non-measurable sets, and we have the algebraic infinity trick. Now let's see how they all come together to actually pull off this heist and assemble two spheres. And get this, a common version of the proof shows that you can pull this whole thing off with as few as 5 pieces. That is it. One sphere, 5 unimaginably complex cuts, and you're ready to double your assets. So here's the process. The sphere's broken down into these 5 ghost-like point clouds. Then, you simply take 2 of the pieces and rotate them. No stretching, no shrinking, you just turn them, and they interlock perfectly to form a complete sphere. Then you do the exact same thing with 2 of the other pieces to make the second sphere. That last piece is really just a few leftover points you pop back in to make the copies perfect. And there you have it, 2 identical spheres from one. So at this point, you are probably thinking, this is absurd. This has to break the laws of physics, right? And you are not wrong to think that. This is precisely why it started a philosophical civil war in mathematics, and also why, thankfully, you can't just do this with your car keys. The controversy basically split mathematicians into two camps. On one side, you had the Platonists. They argued that if the logic is sound, then the paradox is a true feature of the abstract world of mathematics, whether it makes physical sense or not. But on the other side, you had the constructivists. They saw this as proof that the axiom of choice itself was the problem, arguing that any tool that leads to something so physically impossible just had to be rejected.
The reason this can never, ever happen in our universe really comes down to two simple points. First, atomicity. Real objects are made of atoms. You can't make these infinitely precise cuts because eventually you're going to hit an atom. Game over. And second, measurability. Those paradoxical pieces, remember, have no defined volume. But every piece of a real object, no matter how small you cut it, always has some volume. The paradox lives in a pure mathematical world of points, not our messy physical world of matter.
And hey, if you thought doubling a sphere was strange, get this. The same logic proves that you can decompose a single p into a finite number of pieces and reassemble them to form a sphere the size of the sun. And you might ask, how is that even possible? It's because from a purely mathematical perspective, a tiny p and the giant sun are made of the exact same number of points, an uncountable infinity of them. Since the pieces themselves are just collections of points with no volume, ideas like size and scale become totally meaningless.
So in the end, the Banach-Tarski Paradox isn't a flaw in physics. It's actually a beautiful, if a little unsettling, reminder that mathematics is a language. And it's a language capable of describing realities far stranger than the one we live in. Our intuition is built for a world of finite things, but math gives us the tools to explore the infinite.
This all leaves us with a final thought. If the abstract logic of math can lead to something as seemingly impossible as doubling a sphere, it just proves that the world we can imagine is so much vaster than the world we can actually touch. And it forces us to ask, in that huge abstract realm, what other beautiful monsters are just waiting to be discovered?